as Nick said, I'm one of the senior bioinformaticians in the PhD genomics cell. I've been kind of working on the kind of detection and definition of the variants that PHE have declared. So the ones that we've kind of named the kind of VOC and VUI rather than alpha beta, although they generally align, they're not all the same. So yeah, I'm going to kind of go through the methods of detection that we use, the levels of concern, associated public health action that we have at PHE, and then a little bit about how we would go about specifically defining the variants. And so hopefully the stuff that you've heard this morning kind of leads nicely into this. So we have kind of our genomic epidemiology, and we have the lineage naming and the tree phylogeny, all of that kind of stuff. And then, as Anya kind of said, we then start speaking about specific variants rather than lineages. And generally they are associated with a lineage, but not always. So we have at PHE a process called horizon scanning, which is our main sort of function within the genomic cell, and that's our process for sort of monitoring and detecting variants that we think need specific public health action to prevent antigenic escape or prevent the spread of something that we think has high transmissibility, which we've done to some degree, but some things have escaped us nevertheless. So there are kind of four main arms to the horizon scanning that are like routine processes. So the first one is cluster detection, which uses the phylogenetic tree to identify sort of clades and clusters and estimate their growth rates so that we can spot things that look like they're growing faster than other things that are around in the region or in specific places in the UK. And those are kind of paired with genomic and epidemiological information in very much the kind of way that Verity's talk was alluding to, in terms of looking at person, time, place, and then also thinking about like specific mutations and what the kind of surrounding genomics looks like. Does it look like it's an importation, etc., etc.? The next thing is mutation scanning, and we kind of do this in a few different ways, but essentially what we're looking at is things that we know or suspect have either an antigenic or avidity impact. So things like E484K, 501Y, mutations like that you've probably come across with the various different variants that we've already declared. And we also have a process for scoring constellations of mutations. So they have kind of a sort of numeric value depending on the impact that we think they're going to have. And so the combination of those numeric values gives us an idea of how high a specific sequence would rank compared to the variants that we are already monitoring, so that we can spot something new that looks like it would have a similar level of concern to something that we're already monitoring. Then we have specific scans across the GISAID data. So obviously the UK has a very rich genomic data set, but we also want to make sure that we know what else is going on in the rest of the world as best we can, so that if there are specific things of concern in other countries, we can monitor those coming into the UK and try and prevent spread. And it also kind of feeds into, eventually when it comes through horizon scanning, it feeds into kind of our border risk assessments and things like that, so that we can curate the sort of red, amber, green lists that the UK has for travellers. And then we have special groups of interest. So imported cases are kind of an example of those, which I'm specifically involved in, so I can talk to a bit better. But we have kind of special groups of interest. So those are imported cases, but also cases of reinfection or cases in fully vaccinated individuals. So those are obviously, the reinfections and the vaccinations are obviously important for us, because if those people are expected to have some level of immunity, so if they are still infected by something, we want to make sure that we don't think that particular thing has a sufficient level of antigenic escape that it would put pressure on or kind of escape the vaccine, and then we would have this kind of additional wave that we can't kind of combat in the way that we hope in terms of having herd immunity across the country. And then we have kind of various other different ways that things feed in. So it might be some news reports, or somebody in another group. Generally, we follow quite closely the pangolin lineage requests, because those kind of flag things to us that other people have noticed that we might not yet have flagged through our normal processes, because most of these things run once a week. So we have kind of a routine check of all of the other data sources that we have to make sure that we're not kind of missing things or picking them up later than we possibly could. So thinking about all of those different scans, there's obviously a lot of information coming in, and we have to actually decide what we consider to be a signal. And so a signal isn't necessarily something that eventually will become a VOC or VUI. It's just something that we say, this has flagged on a specific criteria, and so we need to look into it in more detail. We now know it exists, and we want to check the epidemiological information, any surrounding sequences. Is it part of a cluster? Is it seen more widely across the GISA data, things like that, so that we can get a better idea of whether this is kind of an isolated incident or we think it's something wider that we need to be concerned about. So there are kind of four main signals that we flag, and the kind of most frequent one is that we have a new mutation constellation with known antigenic or avidity mutations. So this kind of comes back to the scoring thing that I kind of mentioned. So anything that has a high score that we haven't seen before, we would flag as a signal and then investigate that and decide whether it meets our thresholds for monitoring or VOC or VUI. And we use that kind of signal, can come from the UK or GISA data, and it's especially important in our special groups of interest that I mentioned before. Then we have the increase in frequency of a specific mutation. So this might be a mutation that a known variant has acquired. So for example, E484K on top of the alpha variant, that was of specific concern to us. Or it might be in something that we aren't currently monitoring, so not a variant that we've already declared, and we just see this mutation increasing in frequency. And so we'll have a look at the kind of rest of the genome to see what else that specific lineage or cluster has that might mean that it's got a specific advantage, and that's why we're seeing it growing. And then you kind of have the increase in frequency of a constellation in a specific group. So constellations that might not necessarily flag because of a high score, but they're seen in a specific group that we are interested in. So again, the reinfections or the vaccinated individuals, because obviously we don't know everything about every mutation. There are only specific ones that we know about in terms of laboratory information and kind of previous experience. So for example, with the Delta variant, the L452R mutation was kind of on our radar because it's seen in the lineage that we see in California, but that specific lineage wasn't something that we had raised as a particular concern, because although it was successful in California, we didn't actually see it have much success outside of that region. But it didn't score particularly highly, because although we'd seen it before, we hadn't seen something quite as effective as Delta. So it flagged to us because, obviously the epidemiology in India at the time was very bad, but it was a kind of constellation that we hadn't seen before, but we were starting to see it in these kind of special groups and, you know, in imported cases, but also across in kind of clusters. So it flagged in kind of a lot of places. And then the last one is a cluster with a higher growth rate than is expected. So with our cluster scan, we kind of have these growth rate estimates and we kind of compare them or sort of normalize them against each other. So if something looks like it's growing faster than the things around it or other things that we know are successful, then that will flag as a signal because we'll need to investigate why it's particularly successful. And it might be a fairly reasonable explanation. There's some kind of epidemiological factor. So for example, it's a school outbreak. So you have lots of cases from a particular school. And so that looks like a very fast growing cluster, but actually it's because you've got lots of sampling going on in that environment rather than kind of the random surveillance sampling that you see just generally across the country. So the next thing I want to kind of cover is the sort of levels of concern that we have in terms of our horizon scanning and variant detection. So you have this kind of cloud of signals. So there are things that we kind of know about. We've seen them in the horizon scanning, but they haven't really ticked any boxes or hit any thresholds. So we kind of know about them, but at the moment they're not of concern for us. That might change with additional weeks or additional data. So we kind of know about them and they're on our list of things that we've seen before, but they don't necessarily have any intervention or monitoring associated with them. Then you have what we call signals in monitoring. So these are specific signals that we think have the potential to be a variant of interest or of concern, but at the moment are small numbers, or we don't have enough information, we're waiting for some laboratory results, things like that. So we're kind of actively monitoring, so we're actively seeking out cases of those specific variants, but we aren't associating any public health action with them. Then you have your variants under investigation. They are things that we are concerned about, but they don't have sufficient sort of laboratory or confirmed phenotypic information to suggest that they are of specific concern. And then you have your VOCs, which obviously are things that we are particularly concerned about, and if possible, we would like to stamp out, although that doesn't necessarily always happen. Which brings me on to the public health management. So the level of concern about a particular variant is entirely detached from the public health management associated with it. And so we can be extremely concerned about a particular variant, but there may be no public health management action associated with it. For example, Alpha and Delta, because initially, sort of at the beginning of this year, there were so many Alpha cases that although it was a variant that we were concerned about, we kind of missed the boat of public health action because we don't have the resources to stamp it out when you get to that many cases. And then now that's happened with Delta, because the cases are so high, the level of public health management has reduced. So there are 3 levels. One is standard, so that's just the standard COVID-19 management. It will be your isolation, your contacts have to isolate for a certain amount of time. There's no additional action on top of just your normal test and trace. Then you have level 2, which is additional public health management. And so that will have a slightly elevated level of investigation associated with it, and it will inform our risk assessments to decide what we're going to do in a particular area. Are they going to have enhanced testing for a specific site, or do they need to close down bubbles in a school and that kind of thing? And then you'll have some additional control measures associated with that, and that's led by the health protection team. Then you have level 3, which is advanced. So this has a very intense, comprehensive forwards and backwards contact tracing protocol And so that means that they will contact the case, ask them for anyone that they were in contact with prior to their infection so that we can see if there are any positive cases there and try and find the source, and also their forwards contact tracing so that we can stamp out any onwards transmission that's happened. So at the moment, the most kind of successful example of this is our beta and gamma cases. So we are very aggressively contact tracing those to make sure that they don't spread in the community. And to this point, touch wood, we've done that very well. And the reason that we have such extreme action on those is because we have phenotypic evidence that they have a particular antigenic effect. And so we are concerned about vaccine efficacy in these cases. So we really want to make sure that they don't take hold in the UK, because vaccination is obviously a big part of how we're able to open up and reduce the restrictions. So now getting into kind of defining a new variant. So we found our signal, we've reviewed the evidence, and we've decided that actually this is either it's going into one of the three categories. So we might be monitoring it, it might be a VUI, or it might be a VOC. And in all three of those cases, we need a definition so that we can identify the cases as soon as we sequence them and they come through our sort of processing. And there's kind of two sort of things that you need to do initially to actually decide what is included in your variant. So in the kind of tree on the left, the piece in yellow is the specific variant that we want to define in this case, and then the rest of the tree is kind of the wider parent lineage. So in this case, we're kind of trying to define a subgroup in a much larger group, and it might not be particularly clear, but there's one out sequence that's still part of this kind of offshoot from the main ancestor, but actually is not part of the specific clade that we have decided is our interesting signal. So it's kind of deciding where that threshold is and what you want to include or exclude. And so similarly with the tree on the right, but it's kind of in the reverse direction here. So this particular example is a lineage that had already been defined. So this is an example of the Lambda variant, which WHO declared before we declared it a VUI. And so up until that point, we had always declared or were monitoring things before WHO declared them. And this was the first time that it happened the other way around. So in this particular tree, this is all of these sequences have been identified as C37 by pangolin. But if you kind of look at the pieces in the red on this tree, they don't quite fit the clade. And so although they may well be C37 sequences, it might be that they have missing data or the quality of those sequences isn't quite as good. So we need to exclude them from our definition purposes to make sure that what we're defining is as accurate as it can be, and we aren't going to include kind of false positives, especially when you have public health action associated with them, because the HPTs are very, very busy and they have a lot to do. So we want to try and make sure that that action is as specific and targeted as we can, so that we aren't kind of giving them unnecessary work. So once you've decided which sequences you want to include, you have to decide which mutations you're going to include in your definition. And so again, this is the C37. This is the example from the tree that was on the left on the previous slide. And so just in this screenshot that I've picked out, you can kind of see that you've got two mutations that are present in a much larger number of sequences. So everything in our kind of clade of interest is right at the top. And then everything in the wider clade is underneath that. So you don't want to include mutations in your definition that are present in hundreds or maybe even thousands of sequences. So things like D614G, they're not informative positions in terms of a definition. So they're not useful in terms of characterizing a variant because they're present in so many different things. And then when you find your kind of groups of mutations like the 3 in this image here, you have to kind of make a judgment about whether those mutations are going to be informative. So you can kind of see that in this example, it's the specific mutation is missing in sort of 1 or 2 sequences. And you have to make a judgment call in terms of the quality of those sequences and deciding whether it's missing because the data is poor or missing because it actually isn't an informative position. And so you don't want to include something in the definition that isn't informative, because then you're going to reduce your sensitivity and you're going to miss things. But equally, you don't want to throw things out just because you have a sequence that's got a little bit of missing data. So it's a really difficult balance to try and make sure that you have enough sensitivity, but also a good specificity. And that's kind of the hardest part with this sort of definition curation. So that brings me on to kind of the calling definition. So we have 3 categories. The confirmed is at the moment where all of the mutations are present. So everything that we've decided is defining for that variant is present in those sequences. So we are confident that it is that variant. Then we have a probable definition. And so that is your balance between sensitivity and specificity. So you pick a kind of threshold that will give you enough mutations that you can be confident that it is that specific variant, but it's not too high that when you've got poor quality sequences, you can't get any usable information out of them. And that again is a hard balance to strike, and it depends entirely on the variant. Some things are so distinctive that you can set the threshold really low, but some things, especially when you get these kind of convergent evolutions, so you see lots of things that have 484K, 501Y, and that kind of stuff. So you have fewer mutations that are actually informative about your variant, although those mutations are important in terms of why you have declared it a variant. They're not actually useful for identifying which sequences are and are not a specific variant. And the last category is this low QC category, and you can kind of see that all of the mutations required is 0 in this, and that's because we need to be able to capture sequences where we're not able to rule out a variant. Although we can't rule it in, we have to also be able to say this may be that variant, but we don't have enough information to say that, because we want to make sure that there's not an insufficient level of public health management. So if there's sufficient epidemiological information to say, you know, if they're a direct contact of someone that has a known variant and their sequencing comes back and we say this sequencing was inconclusive, they'll rely on the epidemiological information rather than us saying it's not this variant, and then they rule them out of the cluster, but they've kind of done that incorrectly. And you can also see from these definitions that we currently don't allow any wild type calls. And this is kind of a historic thing, but comes back to your kind of sensitivity, or well, more so your specificity, I suppose. So we don't really allow wild type calls because we try to make the definitions fit so that you don't need to have positions plus or minus, because they're not really then defining mutations. But now that we're getting to the point where we have a high number of variants, and as I said, we have these kind of convergent evolution issues where we're actually running out of specific mutations for some of the variants, we might have to start allowing these wild type calls and picking things that are in sort of subclusters of specific variants that we can use in a similar kind of way. So the next thing that we kind of have to do is make sure that we review the definition. So we need to make sure that as the data increases, we're still capturing things effectively. And this is particularly important when we define a variant early on. So if we only have a handful of cases, we may be sampling from a sampling a small section of a very wide pool. And so it's really important that you define it and then you kind of check for any edge cases and make a judgment about why they're edge cases. Is that because they're not the variant, or is it because your definition is too strict, and do you need to kind of reevaluate it and change it slightly so that you capture everything effectively? So in this example, this is lineage B11318. So we kind of reviewed this, looked at things that were not quite meeting the definition, but had all of the hallmarks of being this variant. And there were 2 mutations, one synonymous and one non-synonymous, that were missing in more of the international sequences, so sequences from GISAID, but also a few UK genomes. And so it probably is reflecting some unsampled diversity at the point that we defined this particular variant. So the likelihood is we'd only sampled from this kind of top part of the clade when we created the definition, but actually there was this sort of bottom half that was undersampled that we weren't capturing very effectively. So we had to revise our definition and take those 2 mutations away so that we could still identify the cases that were kind of coming from these outside pieces of the tree sort of thing. We might also want to increase the sensitivity of our definition. So as I said, we have this kind of low QC category where anything that doesn't have a sufficient number of mutations falls into that group. And for anything that is called as low QC, we at PHE, we have a kind of manual review process. So we go through all of the sequences and make a judgment to decide sort of the risk associated with that genome. So obviously, if all of the defining positions are missing, then there's not really a lot that we can say about that. And that goes into our sort of, we can't rule this out kind of bin. But there may be 1 or 2 mutations, or depending on where your threshold's set, there could be quite a few mutations. So this example is the definition that we were using for the Delta variant. And obviously there are 2 other B1617 clades, and some of the mutations that were in the definition are shared between all 3 or with one or the other of those clades. And so that meant that out of the 12 mutations, we had to have at least 8 of them to make sure that we were calling something that was specifically the Delta clade. And that's quite a high threshold, especially when you have quite a few mutations sort of clustered in spike, which we know is kind of problematic in terms of sequencing. So you have several mutations that fall in the same tile. So anytime you get any kind of amplicon dropout, you're immediately missing a good chunk of the mutations that you need to call this. And that meant that we were having to review a lot of sequences. So, you know, we've got to a point where we were trying to review 200 a day, and that's not sustainable for a team that's 4 people. So we looked at the definition to see if we could increase the sensitivity, and the way we've done that is kind of removing some of the mutations that we see dropping out very frequently that aren't really that informative in terms of the actual Delta clade itself. So those were 452R, D950N, and in N, the D377Y mutations. So those were taken out. And that meant that we could reduce our probable threshold from 8 to 4, which is a really drastic decrease, but meant that a lot of the low QC that we were having to review by hand already got swept up into the probable definition, but it didn't reduce our specificity because the only things that we removed were things that actually weren't that informative in terms of the Delta clade anyway. So I've just put together a few do's and don'ts in terms of defining variants. And this is by no means an exhaustive list, but they were just kind of the first ones that came to mind that I think are really important when you're trying to define a new variant. And so that's kind of, in terms of the do's, you need to really clearly define your clade of interest, and equally like revise that clade as time goes on and make sure that you know where the line is for what is and isn't your variant. Make sure you have some good ancestral data, because although if you have your set of sequences, you can say they contain all of the sequences contain these mutations. You need to be able to say which combination of those mutations is actually informative in terms of defining your variant. You don't want to include every single mutation that it has, because then if you set your, as we saw with the delta definition, if you set your probable threshold too high, you're going to find things that contain all of your sort of variant specific mutations, but they don't have enough for you to define them in an automated way. I would also say that it's really important to consider synonymous changes. So although they're not going to be important for you saying these are the reason that we're declaring this variant, they're important in terms of defining it, because they're actually less likely to pop up in other things. So they can be more informative in terms of your definition. And it's really important that you check for false positives. So using the definition, your kind of draft definition, run it against your data set and see if you're picking up anything that actually is not the variant, and how you can refine it to make sure that you have that effective balance of sensitivity and specificity. And then also make sure that you're refreshing and refining your definition as you go along, and that you know where your kind of almost variants are, as we kind of call them. And in terms of your don'ts, the biggest thing is assessing the quality of the genomes that you're looking at, especially when all you have to go on is a FASTA sequence. So you have no raw data to make a judgment on mixed bases or why specific regions are missing. You just have to look at the FASTA sequence and make a decision about whether you think that is a reliable genome. And so if it's missing something, is it missing because that's not an informative position, or is it missing because it's not a very useful sequence? Don't include mutations that you know have an issue. The best example of this is in Delta, the G142D mutation we know is present in Delta, but if you look at the tree, it appears to pop up lots of different times, but that's because there are issues with certain amplicons. That means sometimes you do and don't pick that mutation up. So including that isn't informative in terms of your definition. And so if you know that there's an issue with it, just don't put it in the definition, because it will cause you more problems than you need. Don't include indels, and that is not because they're not informative or not defining, but it's just because they're so difficult to deal with. People call them in different ways. Sometimes they don't call them at all. Sometimes they shift one way or the other. So they just are a big pain. And again, it's going to cause you more issues than it's worth. And then don't set your thresholds too high or too low. And that, again, comes back to your refreshing and refining. If you are consistently looking at your kind of cloud surrounding your definition and looking at what you're calling as the variant and whether that's appropriate, you can kind of get to an appropriate threshold. And that kind of comes with experience as well. Like when we first defined alpha and beta, we were kind of, it was the blind leading the blind sort of, because we'd never done it before. So we did the best we could and have had to kind of refine that over time. But now that we've defined sort of upwards of 15 of these now, you can kind of look at them and you get to know which mutations are going to be problematic. You get to know which mutations appear in lots of things, and you get a sense of what threshold is acceptable and where you can kind of draw the line to make sure that you don't have hundreds and hundreds of low QC to review, but you also don't have a really high false positive rate. So that is kind of everything that I was going to talk about. The only other thing I wanted to point out to everyone is where our current variant definitions live. So we have a GitHub page that contains all of the YAML files. So if you aren't aware of those, feel free to go and have a look. And yeah, if there are any questions, I will answer them.
Brilliant, thank you. Thank you very much. I mean, that is a really good rundown of all of that, like the serious amount of work that goes into both detecting these new variants and then defining them. Having lived through this the last, 6 months or so, I know how much work it's been for the team at PHE to do this, and I think internationally the efforts have been really appreciated in terms of that ability to detect and define these new variants. Let's take some questions from the audience. So Natalie Watt asks, is the scoring of the constellation of mutations based on experimental lab data?
Mostly, yes, but some of it is based also on theoretical modelling, and some of it is also just based on our experience. So if there's things that we see popping up that we don't necessarily know the exact function of, but we get the feeling that it probably is important because we see it come up time and time again in these variants that we're declaring, then we will also kind of rank those, because otherwise we end up missing things just because we don't have any lab data for them. And there's kind of most of the lab data comes from kind of academic groups, and so there's sort of a bit of bias. Once you get something that somebody says has an effect, then you get lots of groups testing the same thing. So we saw that with kind of 501Y and E484K. So we have lots of evidence to support those specific mutations, but there are things in that general region or similar things like E484Q, E484A that we think probably have a similar sort of effect, but we don't have as much lab data to support them. And so we have to kind of make sure that we're not going to miss them, just because of this kind of bias in terms of the phenotypic data that we have.
Yeah, and I mean, it's probably fair to say, isn't it, that most of the experimental data that's available are, about point mutations, couple of point mutations, distance in spike protein, and
yeah,
we don't really have much of a feel about other genes, do we, and mutations in other genes and the potential impact.
No, not really. And again, that comes down to our kind of experience and seeing things that pop up several times. So there's, a few mutations there's one in particular in the M protein that springs to mind, and there's a couple in N that we see in various different variants, but we don't really see them in the kind of general surveillance of stuff. So we kind of know what the kind of hallmarks of a variant are, if you know what I mean.
Yeah. I mean, so much we don't know, I think, about this virus really, and then like things like ORF8, which tends to sort of drop out all the time, and no one really knows what it does and if it's important. It's very, very difficult, this kind of work, I think. Phil asks, so Phil's interested in the role of detailed analysis of mutations compared with epidemiological analysis of increasing case numbers and identifying things we should be concerned about. Although he admits that he skipped a bit of your talk, so you did sort of cover this, but in many settings, when there isn't such good genomic surveillance, not such a great percentage of cases genome sequenced, you have to rely more on mutation analysis. So can you speak to that a bit?
Yeah, I mean, I think, although we have good surveillance in the UK, we do also have that kind of issue, especially when we're looking at the imported genomes. So, we sequence a small proportion of our imported cases, and that's an even smaller proportion of what's circulating in whatever country that person traveled from. So we have to also make those judgment calls if we're importing something. And I guess, again, this kind of comes down to experience. If we see constellations that ring true of a variant, or there's certain things that we look at and kind of send shivers down your spine because they look sufficiently scary, we can make a judgment on those. But I mean, a lot of the time we do have to wait until there is sufficient epidemiological information, and that's not always helpful. But I guess it just comes down to your kind of risk assessment, really. If there's sufficient evidence in the mutations that you should be concerned that actually if it was spreading anywhere, it would be bad, then any cases that you do have, you can identify from genomics, then you declare it and you just stamp it out as quickly as you can, because there's nothing worse than missing the boat, which, you know, we know from experience. So yeah, I'd say if you are relying on mutations, you kind of need to just make a risk assessment, and decide what you want to do. Like sometimes, although you don't have genomic surveillance, you can kind of see an epidemiological signal that fits in terms of time and space as well. So if we have something that we're importing, we'll always get our colleagues in the international epidemiology cell to give us a rundown of what the epidemiology in a certain place is like, so that we can say, okay, we've started to import this several times over this period, and if you look at the epi, there's an uptick in their case numbers that fits with that sort of time frame, and so that kind of lends itself to that kind of assessment as well.
Yeah, I mean, I definitely agree with that. I think that it's really, it's actually really, I mean, it's very easy to make a story about a mutation once you know that it's associated with high growth, but
yeah,
to be really confident that you're going to see a phenotype from a mutation seems to be hard. As you say, there were lots of mutations we tracked, when they're like 484K, that we would assume would pop up and take over, associated with, you know, increased vaccination, increased natural infection, and basically immune escape, but it just didn't happen. And I think probably one thing to say is, obviously countries like the UK that, you know, do a lot of genomic surveillance. I mean, PHE have been fantastic at generating these weekly, now bi-weekly variant technical reports, which go online on the government website. There's a lot of information there to glean in terms of what is happening epidemiologically associated with variants with particular mutations. So that would be a good, you know, in a country where you don't have good genomic surveillance, or can't have good genomic surveillance, probably looking at the experience of other countries, because what we tend to see is what happens in the UK is then replicated in other countries, and particularly sort of UK first, then mainland Europe is a common thing that happens, and also the US. So you know, there is that data sharing is absolutely vital, and also that open analysis. But obviously, I think our view is that everyone should get a certain amount of genomic surveillance done. It doesn't have to be all the cases, doesn't even have to be the majority of cases, but some genomic surveillance is incredibly helpful for linking epi with the mutational profiles. It's hard to do.
Yeah, definitely.
All right, a couple more questions. So Clement is thinking about, I think, rapid genotyping type methods and maybe Sanger sequencing of spike. So if you use targeted methods like that to detect mutations, do lineage identification, presumably there's a chance of misidentification because some mutations appear in different lineages.
Yeah, so I mean, in the UK, we have a rapid genotyping assay now that targets specific variants, and that was a kind of a particular process to kind of design that assay in a way that was specific enough that you could pick up the variants that we wanted to pick up. So it only detects a small number of things that we think are important to know about as early as possible. And there is a chance that there is a misidentification in those, because, like you say, things appear in different lineages over and over again, but we try to pick combinations of things. So the targets are picked in a specific way that that you have a reasonable amount of sensitivity, but we've also kind of accepted that these mutations that do appear in multiple lineages are of concern. So if you pick up additional things and you do that kind of extended forwards and backwards contact tracing, worst case scenario is somebody spent a bit of time doing that, but actually you've still broken down a transmission chain of SARS-CoV-2. So it's not the end of the world that it wasn't your particular variant of concern, because it still had a good result. Obviously, it's just kind of managing the resources. So if that's happening all the time, you need to reevaluate your assay, because you don't want to waste resources doing those kind of things too often. But if you do have the occasional one, it's kind of not the end of the world for us.
Yeah. Okay. Another question from Vinicius is there a more convenient way to visualize trees and shared mutations together to make identifying the new variants easier? Yesterday, Jared presented his NCOV tools package, which shows a tree plus the SNP diagram next to each other to help identify, to visualize that. So have you found any software packages that are kind of useful for this?
No, so if you have them, I would like to have them also. But I mean, we've kind of developed these systems over a long time. So it's kind of an iterative process that we go through. So we have some kind of quite clunky ways of deciding what our clade of interest is, and then, going through the mutation profiles to decide what we think is an informative thing for a definition. But in terms of our detection, generally we rely on just actually looking at a mutation profile, because where it sits in the tree is actually less relevant to us. We just want to know what the mutation profile is, and then we kind of rank those using our kind of scoring system, and we say, okay, this is high at the top, let's look at that in more detail. So then we would go to the tree and say, okay, it's part of a cluster, or it's on a long branch. So that again is indicative of a variant that we would be concerned about. So I think the tree visualization is kind of secondary for us in terms of variant detection, because the mutations is really what we're interested in.
Yeah, I mean, I definitely think that we need more good tools for this. I think like one thing that I always want to do and I find difficult is that ancestral reconstruction is a bit painful to do on the command line, and quite often I will go and use something like NextStrain, because that has quite an easy way of seeing at different nodes in the tree what the SNPs, what the defining SNPs are. But it'd be nice if we could do that more easily.